Hey guys, we were receiving multiple grievances about the sound quality of the STA series from multiple viewers over a long period of time. It took our serious attention. As a solution, we are republishing STA episodes by digitally remastering the audio. In this video, we are clubbing 4 input-output file formats episodes from the STA series. So, stay tuned, stay focused. Hey guys, welcome to the 6th episode of Static Timing Analysis. We have so far talked about the various theoretical concepts. We will be focusing on the STA input files for next couple of episodes, starting from this episode. Today we focus on the very important input file called timing library file. Also, sometimes you call it the .lib file. You can see in the rightmost corner the timing library, that is the Liberty file, is highlighted in green circle. These files have a .lib extension, and these are human readable ASCII file, that is text file in simple language. We are done here, so let's move on. As you already know that we are exploring the timing library file here in this episode. So today's learning breakdown for the episode is how Liberty file is created, Liberty file introduction, Liberty file internal format and sections, internal format, name tokens and their meaning, header, LUT, cell, all this section definition, lookup table, LUT section, various standard cell sections inside the Liberty file with example. We are done with this particular slide, so let's move on. How Liberty file is created. In this slide, we will discuss the Liberty timing library creation in a nutshell. Here are the representation of standard cells logic family. At synthesis level, you first need the gate level netlist for each unit logic gate. These are digital logic gates. We also have the sequential elements such as flip-flop in the standard cell library. Inside the standard cell library, on single cell, we have various views like Verilog, .lib, that is Liberty, layout, DSPF, spice, CDL, schematic, EMIR views, etc. In the standard cell characterization, the engine picks up the necessary views for the characterization and runs the dynamic timing analysis, which is already explained in episode 1. In case you have not seen the episode 1, request you to use the chapter facility in the respective video description to quickly navigate and see the relevant section. Now, the characterization process gives birth to the ST, that is the text output file called the .lib file. Now, let us get a bit closely familiar with this file. Let me give you the brief introduction to the .lib file used in the static timing analysis. Timing engine reads a set of cells library files, that is .lib file. So this is meant to say that the timing engine could read more than one .lib file depending on your design in actual vlsi chip making area. The .lib file is a text file containing timing and power parameters associated with any standard cell for a given technology node. Now here one term I would like to explain, that is the technology node. You might have heard it's a 2 nanometer chip, or it's a 5 nanometer chip, or it's a 10 nanometer chip. So this nanometer number that you are getting nowadays on the chip is the technology node. However, each company has their own method to describe this technology node. You can take the ITRS technology roadmap for a standard where they define that the technology node, that is the nanometer that we speak for any of the chip, is the DRAM half pitch. So the distance between the DRAM half pitch is called technology node as per the ITRS guidelines. Now the .lib file contains not only timing but it also contains the power parameters. That is one more thing you getting to know here. And this .lib for a technology node will contain the exhaustive list for the timing and power parameters for all the logic gates, sequential cells, etc. And there will be a couple of special cells also. Those special cells I have explained in the UPF video. You can go there and see. Also, I will put the link in the description. It contains the data for all standard cells available in the design in the specified technology node. I have just mentioned it. So each instance in the Verilog VHDL or system Verilog netlist must have a corresponding cell found in the .lib library. So guys, whenever you are reading the files inside your timing engine, there you load your Verilog file, then you load your .lib file. So that loading of these files will go to the temporary live database, that is the design database, that is with the timing shell, that will automatically map the corresponding Verilog and its corresponding cell section from the .lib file. It will do with its intelligence. The .lib file contains pre-characterized timing models and data to calculate IO path delay, timing check values, and interconnect delays. So whatever data we have in the .lib file, they can calculate all these things. To compensate the PVT and OCV variation, derating factors are also included. I have already explained in some of the previous episodes about this PVT and OCV variation separately in detail. So all those derating factors means when this variation happens, we include derating factor so that we can actualize the PVT and OCV variation inside the static timing analysis. We are done with this particular slide, so let's move on. Liberty internal format. Let's look into the internal structure of the Liberty file. If you directly open the .lib file with any text editor such as gvim or gedit, etc., what you will see, the vastness of the data mining inside the file. The data mining is done in a very efficient structural format. We can broadly classify the content inside a .liberty file in 3 broad sections and their subsections. So the sections are like this. There will be a header section, the LUT, that is lookup table section, and third, the cell definition. So these are major sections inside the .lib file. And in this presentation, I will go to the definition plus example of all of these sections in upcoming slides. So you are done with this particular slide. So let's move on. Name tokens and their meaning. Before jumping into each section and analyze them in detail, let us get familiar with few frequently used name tokens and their meaning. These have very straightforward meaning. Some of them I have already explained theoretically in some of the previous episodes. So here we go. Norm temperature and norm voltage. These two name token specifies the temperature and voltage reference points, that is operating condition. Slew and delay threshold points. Low and high threshold values for slew calculation, 10% to 90%, and the threshold for delay calculation, that is 50%. I have pictorially made these things clear in previous episodes. These name tokens will be there in the .lib file to specify these 1090 or 80-20 threshold, and the delay threshold will be 50%. Default values for fan-out capacitance slew specifies the limits of maximum input slew on an input pin, input in-out pin capacitance, and the maximum output capacitance on any output pin units. So these name tokens also be there, and from there you can interpret the values. So we are done with this slide. So let's move on. In this slide, we continue further for some more frequently used name tokens and their meaning. Operating conditions, derating factors, limits, and units. 3 different values are usually required, that is typical, worst, and best case. These tokens will be also there, but their values will be typically 3 values, typical, worst, and best. However, to accurately get these 3 values, process parameters and transistor models for the entire process are required, which is only available through Foundry provided PDK or TIC files and used during the pre-characterization stage. So a couple of slides back, I have mentioned that you get the PDK and the TIC files from where the relevant files are picked up automatically during the characterization stage. Here we are re-emphasizing on this point. library and delay model. Provide a library name and delay model to the table lookup, that is non-linear delay model. So some of the LUT I have already explained in couple of previous episodes, but since I am explaining the .live or the timing library in general in this slide, so here I re-specify or re-emphasize these details. Norm process property. Specify the reference points for process scaling used for the characterization of the cells. So these will give the scaling factors of the process. So these are very straightforward, so I'm not going in detail, and you will come across in the example all of these name tokens. Why we call them name tokens? The reason is that these will be fixed text in the .live file, and these text will be fixed across multiple .live files, and they will have a value which may vary from one .live file to another .live file. But these name tokens will be fixed text phrases. I have already explained all of the common type of name tokens in the last two slides, so we are done here. Let's move on. Header section definition. The header section of the timing library file is important for both the STA tool as well as the engineer who is doing the STA. Now, let us see the header section in generalized prototype. We start with the library name. In the angle bracket, the library name will be there. Then starts the header section. Here you can see the slash star, and the star slash acts like a comment in the .live file. There will be delay model. The delay model is table lookup, that is LUT. Time unit, it will be given the time unit in second or nanosecond or something like that. Voltage unit, it will contain the voltage unit. There will be current unit. There will be capacitive load unit. Sometimes we called the load, which also means the capacitance. So that will have its unit here. It has two parts. One is the float, another one is the unit. Leakage power unit, pulling resistive unit will also contain the resistance unit. Then there will be norm process. There will be some double here. It is, you can say, the double real int, that double here we are mentioning. Norm temperature double, norm voltage double, operating condition. In the angle bracket there will be actual instance name. Process double, temperature double, voltage will be double. We close the operating conditions here, and default operating conditions there will be an instance name. So this is the kind of detail of a header section that will what the details it will contain. Sometimes in the library file there could be some additional name tokens. In that case you have to interpret by the name and the meaning. I am done with this particular slide, so let's move on. LUT definition. LUT is lookup table. The body of the Liberty timing library contains lookup table and cell definition. The lookup table or the LUT has a prototype defined in the topmost sections in the Liberty file and just after the header section. So here we define the prototype and later on we use it. You must remember the variable values are subject to change in the data populated LUT inside timing block of each cell definition section. So here we are starting the LUT prototype definition. Lookup table template definition. This is a comment. LUT table template, and there will be the table label or the name. Variable 1, then variable name. This will be a text. Index 1, string of the data points for variable 1. So if this variable have 5 different values, then there will be 5 values mentioned inside this index 1 values section. Variable 2, the variable name, and similarly it will have the index 2 and set of data points for variable 2. And here we close the LUT table template. And further such more template definition will follow. Such multiple LUTs are defined for each particular dataset at the beginning of the library file. Just for example, I can say that you are having multiple LUT template. One thing could be for delay, one thing could be for rise, one thing could be for fall. We will come and see the examples later on today's episode. We are done with this particular slide, so let's move on. Standard cell definition. For each standard cell, we have a standard data structure for its data mining purpose. In this slide, you will get familiar with this general structure. Here was our comment, cell definition, then cell, then cell type, pin name, direction. So here just I would like to emphasize cell type means whether it will contain the name. From that you can check whether it's a logic family or it's a sequential or it's a latch, etc. or it's a special cell. Now we continue again. Clock, that will be Boolean. Max capacitance will be there, that will be a double value. Mean capacitance, that will also again a double value. So these are the upper and lower cap. Then starts the timing block, related pin, then it will be pin name. So this is very much important. Now if you look here, we already started with a pin. Pin means the cell pin on which we are having all this data. And timing is always between two pins. Whatever AT, RAT we define, that is between the two pins. And here the pin and the related pin are the 2 points in between which we are having the timing data. So these two are very important. Combinational or sequential definitions will come in the next section depending upon the cell is a combinational type or a sequential type. Then we close the timing. There could be more timing definitions. As per the number of pins, the more pin sections will follow. Here goes our more pin definitions that I was talking about, and the more timing definition will contain the details of the timing. From here we close curly bracket, we have closed the cell, and the next we have more cell definitions now, and then we totally close here. So this is the kind of cell type definition, and this is a typical structure you will have inside the LUT. Whatever the cell type is, whether it's a logic family or it is a sequential or it's a latch or it's a special cell, there will be cell section. This is must. One more thing not shown here is the functionality. This is a section that contains the truth table representation for combinational cells and present state versus next state table for the sequential cell. This is well understood by any human eyes. We're done with this particular slide, so let's move on. Flip-flop and latch definition. Now, let us have a quick look into the flip-flops and latch structures. The same structure is applicable for all general flip-flops. Flip-flop, state of non-inverting output and state of inverting output. Clocked on, then there will be a clock pin name. Next state, input combination that produces the next state. This is typically looks like a equation. Clear, active value of the clear input. Preset, active value of the preset input. Clear preset variable 1, value of non-inverting output when both are active. Clear preset variable 2, value of the inverting output when both active. Here we close the flip-flop. Latch. Latch is very similar structure but requires enable and data instead of the clock and the next state. So this is a kind of general structure for the flip-flop and latches. We're done with this particular slide. Let's move on. Scan chain cell definition. Apart from the regular cells, special cells which are used in the DFT purpose are included in the library file or the timing library file. These are termed as scan chain cells. We also have scan flip-flop in the timing library file. Let us see the scan chain cell structure. Requires a test cell group to be defined. So this is about the structuring of the .lib file. Two flip-flop groups need to be defined, one in the cell function defined with testing features and one inside the test cell group without the testing feature. So there will be two sections where we have the presence. Test cell. Then come test scan in. Scan input pin name here was. Test scan inverted. Inverted scan input. Test scan out, scan output pin. Test scan output inverted, that is inverted scan output. Test scan enable, high on this pin puts in the test mode. Scan and shift. Test scan enable inverted, same as above but inverted. Test scan clock. The test scan clock for clock scan, and here we close the test cell. So there will be two instances, one inside the test cell group, another in the regular section. So thus the scan chains are defined. One thing we mention here that the scan flip-flop have the similar structure as regular flip-flop mentioned in the last slide, and these are used in the testing purpose of the chip. So we are done with this particular slide, so let's move on. Let's see some example. We came across all the definition blocks so far. Now let us plunge into the examples to fortify our knowledge gained so far with example. Header section. In this and next slide, we will exemplify the header section. So here we start the library simple. Here you are getting the example. So actual names and values will be there. Delay model, table lookup, time unit 1 PS, voltage unit 1 V, there is 1 volt, current unit 1 milliampere, leakage power unit 1 microwatt, capacitive load unit. It has two parts if you remember. First one is 1 and second one is FF. Cooling resistance unit 1 kilo ohm, default fan out load 1.0, default in-out pin capacitance 0.0, default input pin capacitance 0.0, default output pin capacitance 0.0. We continue again. Slew load threshold PCT rise 20.0, slew lower threshold PCT fall 20.0, slew upper threshold PCT rise 80.0, slew upper threshold PCT fall 80.0. So here in these 4 lines we have just explained the thresholds, that is 20, 80 in the slew. Input threshold PCT rise 50.0, input threshold PCT fall 50.0, output threshold PCT rise 50.0, output threshold PCT fall 50.0, norm voltage 0.7, norm temperature 70.0, norm process 1.0. So I would like to mention one thing. Here you can see that in the right hand section, you can see rise, fall, rise, fall, rise, fall for all of these thresholds. This is because in actual transitions, the inclination of the rise or the slew transition may not be same. So explicitly we define here both of them. So we are done with this example of the header section here, and we have it continued in this slide. Operating condition typical underscore 1.0, process 1.00, temperature 70.0, voltage 0.7, pre-type balance tree. We close the operating conditions. So here you can see the operating conditions as process temperature voltage, that is PVT values. Default operating conditions typical 1.0, LU table template delay output slew template 7/8, variable 1 total output net capacitance, variable 2 is input net transition, then comes the variation of the variable 1, that is index 1 means the total output net capacitance. These will be the values on which we have done the variation. Index 2 have a set of variation values here, and we close the LU table template. In upcoming sections, this particular LU table template will not be mentioned. Only the explicit table will be there. So there only index 1, index 2 or variable 1, variable 2 will be mentioned, but these names will not be there. I emphasize the names will not be there in the example in upcoming slides. And another thing in the above section, in the operating conditions, we have kept 1. There could be more than 1, and the default one will be picked up by the default operating conditions. We are done with this particular slide, so let's move on. Cell begin and n. Each cell contains huge amount of data that varies from one cell to another. So we will segregate each section and look into them separately. Here in this slide, we will look into the beginning and end block of any cell because this part will be common. So the begin section of the cell, here goes our example. Begin cell, this is a comment inverter x1. So it's an instance name x1 and the type is inverter. Cell inverter underscore x1. Then pin O, direction output, capacitance 0.0, max capacitance 12.80. Now here we define the capacitance values and the capacitance unit already we have defined in the header section. Mean capacitance is 0.0. Start timing. After these definitions, the timing section inside the cell will begin. Now we see the end part of the cell. Related pin A. This is very important. I have already mentioned because when you talk about one particular pin O, we just kept in the left hand section. The timing always required 2 pins, from and to. So these are those 2 pins. One is the pin which we are having the definition for, and the timing is related with respect to the pin A. Here we close the timing, end of the timing. We go here, end pin, the pin is closed. Next, the next pin comes, pin A, because it's an inverter. There are only 2 pins, one is O and another one is A. It has capacitance 1.0. direction input, and we close pin A. We end pin here. So these are comments. The star slash star and then the star slash defines the comment. We close it and then we close the entire cell, end cell inverter underscore x1. So thus the beginning and the end of each cell will be there. Inside the timing block, there will be relevant timing data. Since we cannot show in one single slide everything here, so that's why I have made the split into 2. One is the begin and end section of a cell, and the respective timing section I will describe in the subsequent slides. As you can see that we describe each pin separately of a cell. The token related pin at every LUT section will connect the timing path between the 2 pins. We will see in upcoming slides. We are done with this particular slide, so let's move on. Before beginning, I would like to mention that here index 1 and index 2 we have described already in the header section. Index 1 is the total output net capacitance and index is the input net transition. These two are also called the output load and the input Q respectively. And here we start our cell output rise delay, the LUT lookup table. Cell rise delay output slew template 7/8. 7/8 gives the number of the row versus column of the table. Here goes our actual index values for index 1. I have mentioned already the index 1 and the index 2 just few minutes back. Index 2 has these all variations, and here goes our table. First row, second row, and we keep on adding the rows and the columns. Here our table gets closed and you can see. So let me bring my mouse. Here goes our row values and here goes our column values. That means index 1 and index 2. Here we close the entire cell rise, the delay output slew template. LUT section we have closed. Cell output rise delay of pin O with respect to pin A. Here related pin is A. This is a kind of I have emphasized here. I have already told, but I have emphasized here just to knock into your mind that the timing is always in between 2 pins, and we just started to describe the O. We left the timing section blank there. We have just kept beginning of a cell and end of a cell, and here now we are defining the timings inside each cell. Cell output fall delay LUT. Starts the timing. Cell fall delay output slew template 7/8. We have index 1 variation, index 2 variation, and here starts our table. Here starts our row, and we keep on adding the rows and corresponding columns, and here we close the table. Now, why I am showing all these explicit examples? Because in our actual .lib file, that is Liberty timing file, all these kind of various lookup tables will be present. So I'm kind of knocking into your mind and with the example, so that you remember when you open and read a .lib file and you don't feel lost in the data. Yes, this all type of LUTs will be there. We close it here, and again re-emphasizing the point that this is the still output fault delay for pin with respect to pin A, which we denote with the related pin name token, and the value is A. So we are done with this example. So let's move on. Cell Output-RiseSlew LUT. Rise transition, delay output Q 7/8. Here goes our index 1 variations. Here goes our index 2 variations. Values, start our row, and we keep on adding the rows and corresponding columns. And here we close the table. And here we close the rise transition block. So this is the LUT for rise transition, that is RiseSlew. Cell output rise time of pin O. We are done. I have not talked much because I have already talked and explained in previous examples. So you can understand by your own about these names. And I have also mentioned earlier that rise and fall will be there because the slanting of the rise and fall transitions are not same in actual transitions, and hence explicit data for rise and fall will be there. We're done with this slide. Let's move on. Cell Output-FallSlew LUT. Fall transition, delay output table template 7/8. Now here goes our index variation, index 2 variation. We start the table values, first row, and then we keep on adding the rows, and the corresponding columns are automatically added. And here we close the table, and here we close the fall transition block. Again emphasizing till output fall time of pin O. We are done with this slide, so let's move on. Hey guys, welcome to the 7th episode of Static Timing Analysis. In today's episode, we will discuss about the Design Constraint File. This is a very important file because here we define the AT and RAT, which we have discussed in episode 1. Constraints are first defined in the synthesis stage, then they are reused in the pre-layout and post-layout SEA. The constraints make a realistic periphery of the ideal netlist. Let me introduce the constraints to you to today's menu. First, we talk about why we write constraints. Then, Design Constraint File introduction will be there. Frequently used design constraint commands will be introduced to you. We will recall the Directed Acyclic Graph concept. Arrival time, input delay. Required arrival time, output delay. Everything is in terms of the constraints. Rise or fall slew design constraint. So this is the menu for today. So without any further delay, let's begin. Why we write constraints? Theoretically, I have already explained that the constraints make a realistic boundary to the ideal netlist during the simulation. We do this in bits and pieces. Let me walk you through such cases as an introduction. By default, in your design, the signal arrives at the input port at time equal to 0. In realistic cases, input signals arrive with a delay added to it. We can do such case by set input delay. We give a value here 2.5. Then we mention for which clock, that is dash clock, CLK, and for all inputs. The overall delay will be 2 nanoseconds relative to the system clock. Thus, you can see first your system was very much ideal. Then we have given this command with a particular delay value to the input, and that makes the system perform like a real case. How to control the output delay? Well, we can do that. Let's see how. Assume that your design is driving a flip-flop. We want to add an output delay on the output pins of 1.5 nanosecond relative to the system clock. So how we do it? We can do such by the command set output delay, and we mention the value 1.5 and we mention for which clock that is CLK and for all outputs. So this is how we can define the delay that is for input and as well as for the output. The purpose of this slide is just to touch base the basic concept of constraints and how the constraints transform an ideal case to a realistic case. I think that is being imprinted into your mind with this particular slide. So let's move on. Design Constraint File. We have understood what is constraint and what purpose it is used for through small examples in last slide. In this slide, let me give you a compact introduction to the Design Constraint File. So here we go. Design Constraint File, also known as SDC files, to impose initial timing conditions on the design. Adding constraint to the design is a process to make your design perform like a realistic situation, which I have been telling for last few minutes. Design Constraint File have an .sdc file extension. Design constraint is a tickle-based format to specify the design intent and the surrounding constraints for synthesis, clocking, timing, power, test, and area. This is a very important point. All the design constraint commands are nothing but tickle procedures. In the tickle series, I have already explained how the tickle works for vlsi. In case you have not watched that episode, I'll provide the link in the description. So guys, all these tickle commands are custom-made tickle procedures and they are very much intended application so that one particular command will do one thing. If you know tickle, you will be very easily write the tickle constraints based on the definitions that are provided in the manual. So guys, I think in upcoming examples, your mind will be very much clear that these are tickle commands and how we are using them. It can be generated during the synthesis stage using the tickle command. Write SDC, then the path, and then the name of the file .sdc. So this is a very widely used command, and this command is used at the synthesis stage to dump all the constraint into a file. We can write the constraint as well as we can dump the constraint. All depends upon the tool which you are using. So don't think I'm making a global comment, but generally tools have this capability to read the SDC and write the SDC at synthesis stage, and it may vary from one vendor to another vendor. But just for your knowledge purpose, we are adding a fact that apart from writing it by hand, you can dump it also. Also, one can create the .sdc file manually in a text editor such as gvin, gedit, nano, notepad++. So I don't know which of text editor you are preferring. You can write down in the comment below which text editor you are very much comfortable with. And generally all these text editors nowadays have the highlighting capability. That means if you are using tickle, they will highlight the tickle proper names and keywords etc. in a different color and your normal values in a different color. So at least what I can say that you can write the commands manually and give it as an input to the tool, or you can dump it using the command just mentioned above. So I think we are done with this slide. Let's move on. Frequently used commands. Let me share a few design constraint commands that a designer very frequently have to use. You may consider this slide as your handbook. So here is our table. So let me bring my mouse. Set input delay. So this is a timing constraint and it sets the input delay of an input port relative to the clock signal. It's very straightforward in meaning, so I am not going any further explanation. Set output delay. This is also a timing constraint. It sets the output delay of an output port relative to a clock signal. So you have a clock in both the cases, and with these two commands you can set the input delay as well as the output delay. One thing I'd like to mention here, whichever tool you are using, just consult the manual for the rest of the arguments of this command. That does make a sense, and that is very much needed because when you are writing this file, those you have to write in a correct way so that whatever your thought process is to implement the constraint, that should be well reflected in the command. Now the third one, create clock. This is also a timing constraint. Creates a clock and defines its waveform in the current design. Set input transition. This is a system interface. Sets a fixed transition time on an input port. So this is basically a transition time, means that the slant, that means the rising or the falling. Set input transition, I think sets the load capacitance value on the output port. Here I think I have done some typo. I'll provide some more corrections in the description. So basically there is another command which is used for the load capacitance value for the output port. So I think the command would be something like that, set output load or something like that. These all commands are kind of frequently used command, and you can take them as for your handbook or something like that. You can write it somewhere in your notebook where all these commands and their arguments, so that you can easily use them whenever you are dealing with your actual design. Let me go to the next slide. some more commands. So far, we have discussed the most frequent commands. Now, in this slide, I will share some names of the commands which self-explanatory nomenclature. Some of these commands you may connect back with the ACA theories that I have covered in all of the previous episodes so far. So, here we go for the list. Set clock, set clock delay, set current design, set false path, set input delay, set IO standard, set multi-cycle path, set output delay, set path delay, set range input delay, set range output delay. So all these names are kind of self-explanatory. You can easily understand and consult the manual whenever needed. The tickle commands are nothing but tickle procedures. So in different vendor tools, they can have a little bit difference in their names. Let me describe it to you. Generally, the commands are set underscore then do something. If you look at the left side list, these are all like that. But in some other simulator, they can be like this. In some simulator, the commands may start with define, then underscore, then do some. So instead of set, it could be define. It may vary from one simulator to another simulator, but the purpose remains the same. If you are encountering a different simulator, not only the name, the arguments may have been a bit different. So be careful and consult the manual every time. We are done with this particular slide. So let's move on. Recall the directed acyclic graph. So these are numbers, just don't panic. This slide is to give you a quick recall of the AT-RAT concept. Here goes our diagram and you can see the numbers and everything has been well fitted inside it. Here goes our definition. Here goes our AT-RAT calculation, which we have discussed in episode 1. In case you have not seen or want to refresh your knowledge, use the chapter facility provided in the episode 1 description to quickly navigate to the respective slide. Link of episode 1 is provided in the description. So let's move on to the next slide. Arrival time, that is input delay. We just pictorially touch based the AT-RAT concept which was discussed in detail in episode 1. Now let me show you how you can define the arrival time, that is input delay. Here goes our example. Create a clock, first thing. Create clock, then we specify the period 50, then name my clock, and then we use rectangular bracket as we use in tickle. Get ports my clock. So we get all the ports and onto that we apply the period and everything. This is how we define create clock. Again, I am emphasizing from one simulator to another simulator, this particular command may be a bit different. So don't panic, always consult the manual. Defining input arrival time, that is AT. Set input delay 0 minimum, then rise for the ports get ports my clock. So here we set the rise time delay. Clock is my clock. Here the delay is 0. Set input delay 25, that is minimum, that is dash fall for falling edges. Get ports my clock to get all the ports of this clock, and then clock name is my clock. Set input delay 0 max, that is rise. This is for rise transition. Get ports my clock and clock name is my clock. Again, we have set input delay 25 max for fall and get ports all the ports of my clock and the clock name is my clock. So here you can say, let me bring my mouse. You can see that we have first defined the two minimums and then we have defined the maximum of rise and fall, rise and fall. So all these rise and fall transition, we have defined the mean and max, the mean and max transitions. So this is how we create a realistic boundary that I have just spoke in the first slide. So we are done with this particular slide. So let's move on. Required arrival time, that is output delay. In this slide, I will exemplify command to define the required arrival time, that is output delay. Here goes our example. Define the output required arrival time, that is RAT. Set output delay 10, then we use the dash mean for minimum and rise, and then we use the get ports of out and clock name my clock. So here we are getting on the ports with out name and applying the delay of 10 for rise transition. Set output delay 10 minimum, and for fall transitions get ports, we get all the ports here through this command for out, and we set clock as my clock. Now we going for the max. Okay, yeah, set output delay 30 max, then for rise transition, and we use the get ports and clock is my clock. Set output delay 30 max, and then for fault transition and get ports for out and clock on my clock. So let me bring my mouse pointer again. If you compare, this remains static, this remains static. Only the changes here it is static and here it is static. Only changes is here and here. So we have couple of combinations just to declare the minimum and maximum of the delays for rise and fall type. So we have 4 total commands to define the realistic boundary for RAT, that is required arrival time. Here we are done with this particular slide. So let's move on. Rise, fall, slew design constraint. In this slide, we are going to exemplify the rise and fall slew constraints through commands. Here goes our example. Define the input transition time. Set input transition 10, then minimum, then rise, then get ports of input and clock is my clock. Set input transition 15, minimum for fall type transition, get ports for input and then clock my clock. Set input transition 20, max, rise, get ports for input and clock is my clock. And we define the set input transition 25, max, and for fall transition, get all the ports input and then clock is my clock. So again, let me bring my mouse pointer. You can see the values are different. Each value is different from one another. And here 2 are mean, these are 2 static, these are 2 static, but this is varying, here this is varying. So rise, rise, fall, fall, and here it is static, here it is static. So this is how we are defining the constraint for the input transition time. One more thing here I would like to add. Here we have defined with 1, but for your case you have to write multiple times for multiple cases, so it depends from one design to another design. So guys, we are done with this particular slide, so let's move on. Some more applications. Apart from the timing, we can do something with the design constraints commands. Let me show you how. Set realistic loads on each output pin. Set load 0.15 to all my outputs. This is how we can also add a load value. Set fan in and fan out for the input or output pins of your design. Set max fan out 1 to all of my outputs. So this rectangular bracket is a typical concept. Now let us define the corresponding load. Set fan out load 8 for all of my outputs. So this way we can use the design constraint. Apart from the timing things, we can define the load, fan out, fan in. We can consult the manual for all these types of other things that you can play around with the constraints. We are done with this slide, so let's move on. Hello and welcome to the 8th episode of Static Timing Analysis. In today's episode, we will discuss about SPEF file. This file contains the details of the parasitics such as resistor, capacitor, and coupling capacitor due to the metal or via interconnection during the place and route stage. These parasitics contribute to RC delay, which in turn can affect the RAT calculations. Thus, the SPEF file is very much important for the STA analysis. Here is our menu for today. First, we discuss the introduction to the SPEF. Next, post-layout parasitics visualization, extraction, position in the ASIC design flow, SPEF and the entire design, various sections of a SPEF file, details of each section of a SPEF file with example. Overall, standard parasitic extraction format snippet. This is basically a short and sweet example of an entire SPEF. So we are done with this particular slide, so let's move on. Introduction to SPEF. Now, let us have a general introduction to the SPEF file. Standard parasitic exchange format, SPEF, is an IEEE standard for representing parasitic data of wires or nets in a chip in ASCII format. That means it's a human readable format. Metal or via in routing have parasitic resistance, capacitance, coupling capacitance associated that are captured by SPEF. These nets also have inductance that is excluded in SPEF. SPEF is used for delay calculation, signal integrity check, crosstalk analysis, EMIR analysis of a chip, which eventually determines its speed of operation. This file cannot be hand created. So this is a very important point. We cannot write a SPEF file by our own hand. This file is created using industry standard extraction engine. It's very much important in the design flow where we are placing the extraction. You will see that at what stage this extraction is done and how critical that stage is. So we cannot write the SPEF file by hand. So we are done with this particular slide. So let's move on. Post layout parasitic visualization. In this slide, you are going to visualize the difference that the SPEF file makes on top of the actual design. In this slide, we will overlay the content of a SPEF file over our design. This slide is for educational explanation purpose. Hence, the circuit diagram are kept over simplified format so that you can grab the meaning quickly and easily. This is our pre-layout synthesized netlist. You can see that these are several logic gates and their interconnection. Now, this is the post-layout parasitic RC annotated netlist. Can you spot the difference? Yes. This and this. These are parasitic resistors which are contributed by the SPEF file. Now you can see that the number of nodes have increased in the circuit. This increment is due to the addition of the parasitics. For simplicity of the diagram, we have not shown the parasitic capacitors. The added nodes are often called subnodes because these expands the existing node into many more new nodes. One another avatar of the SPEF file is SBPF, which is binary file and hence cannot be read by human being. This is for the STA tool consumption only. For very large design, SBPF is useful because of its faster loading time. Now, one thing I would like to say before concluding, this annotation is done by some of the EDA tools. The SPEF file contains the information of these additional parasitic RNCs. Those are highlighted in this diagram. So we are done with this particular slide. So let's move on. Extraction ASIC design flow. Since already I have mentioned that the SPEF file cannot be hand created, you must know at which stage of the vlsi ASIC design the SPEF file is generated. I will describe the ASIC flow and point out the stage where the SPEF file is generated. This will make things clear for you into your mind. Here we start. First, we have the design specification, and in this direction the flow is going forward. Next, we have the RTL coding, which you know, that is HDL coding. Next comes the verification. Next comes the synthesis stage. Next to it, we are entering into the backend stage, that is power routing, and sometimes there could be a pre-layout STA just between these synthesis and power routing. Next comes the global placement. Next to it comes the detailed placement. Next, we have the clock tree synthesis. We have covered this column, so we'll move on to the right hand side. The next is global and detailed routing. We will proceed in the upward direction now. The next is layout generation or changes. Next to it, we do the DRC and LBS of the generated layout. Next, we have the parasitic extraction, that is PEX. At this stage, we extract the SPEF file. Next, we have the static timing analysis, that is post-layout static timing analysis. Next, we go for the EM and IR verification or EM-IR analysis. Next, we do the AEC and final tape-out checks. And finally, the design is ready for tape-out. So folks, you have noticed that, let me bring my mouse pointer here. So these are the front end stage, and here it is entering the back end, and after so many steps comes the parasitic extraction stage. Here we extract the SPEF file. So it is so many level down. So at this stage it is very critical because now you have all the previous steps done and sometimes each of these steps may iterate one more time because to eliminate the errors. So multiple times these steps can iterate and or reiterate, and finally when we come up to this stage we have consumed a huge time. So at this stage we extract the parasitic extraction. So at this stage this is very crucial design turnaround time, and at this stage we extract the SPEF. This guides you one more thing, that the SPEF, if we try to hand create, we cannot, because there are a lot of dependency here, so many steps before this, so we cannot create it by hand. Whatever we create by hand is at the very beginning when we are at here. Okay, something at this stage, maybe in front end something we can hand create, but after crossing so many steps we cannot do anything by hand creation. Everything has to be as per the design flow and through the proper tools, that is EDA tools. So guys, we are done with this particular slide, so let's move on. SPEF and the entire design. You may wonder that we have taken care of the parasitics of the metal via interconnection through SPEFs. An obvious question comes, what is about the interconnection inside each standard cells? Here goes our diagram. As you can see that the standard cells are interconnected by nets. The PEX file, that is SPEF file for net, is called PEF. Similarly, the PEX file for the cells are extracted in DSPF format. These are used during the standard cell characterization to calculate the internal delay. The delay and timing data for these cells are captured in the timing library file, that is .lib file. We have covered this file in detail in one of the previous episodes of this series. I'll provide the link in the description. So guys, if I bring my mouse pointer here, all these nets which are interconnecting the standard cells in the design, they will go to the SPEF. So when they go to the SPEF, each net will have its R and C, the parasitic R and C, all those data will go to SPEF. And the design have the standard cells, all those cells have their respective DSPF file where they have their parasitic data. But whenever we use the static timing analysis, we are concerned about these nets because these cells have already characterized and their data for timing is already captured in the .lib file. So we are done with this particular slide, so let's move on. Various sections of a SPEF file. The SPEF file is a very large file with huge amount of data. However, it is divided into 4 distinct sections for clear interpretation of the huge amount of data. Here are the 4 sections. The first section is a header. The next section is name map. The next section to it is the port section. And finally, we contain all the parasitic information of resistor, capacitor and coupling capacitor in the RCCC section. In upcoming slides, we will describe each of these sections with definition and example. We will append one more optional section called layer map in the last slide of this video. The purpose of this slide is to imprint the 4 sections before we plunge into the detail. We are done with this particular slide, so let's move on. Header section. As the name suggests, this section resides at the top of the SPEF file. However, we do not have a footer section in SPEF file. Header section is a kind of identity card of the SPEF file. Let us see in detail. The header section contains information about design name, the parasitic extraction engine name, naming convention and units. So let us see the thing with an example. First, it goes the first line of the header, that is SPEF, and it gives the IEEE version. Next goes the design name. Here it is XA5017. By the way, all these data are imaginary data. These are not from any actual data or design. So date is something here, the date on which this file was generated. Vendor is ABC Imaginary Corporation. Program is the parasitic generator. Here the name of the parasitic extraction engine will come. Version 0.0. Design flow netlist type Verilog. This has a specific data of values. You can consult the respective extraction engines manual for this particular field. Next comes the divider. Divider means it's a hierarchy separator. If the design is a hierarchical design, the text will be separated for each hierarchy with this particular delimiter. Next comes the delimiter. That is a usual text delimiter. Bus delimiter is the rectangular brackets. Time unit is 1 picosecond. Capacitor unit is 1 femtofarad. Resistance unit is 1 kilo ohm. And L unit, that is inductance unit, is 1 microhenry. Although we have kept it here, but generally in practice the inductor is not present. So we are done with this particular slide. So let's move on. Name map section. For multi-million gate design, the SPEF file will contain huge number of nets interconnecting them. Thus, the SPEF will be very bulky. The name map section provides a way to use shorthand method for net names, which are usually very long for a hierarchical design. Thus, to reduce the overall file size. Let us see how. To reduce the overall file size, SPEF convention is to convert long name of the nets to be mapped to a shorter numbers preceded by an asterisk. The mapping or lookup table is defined in the name map section. Here goes our example. Start the star, then in all caps the name underscore map starts the section. Next comes the 509 is the mapping number, and the actual net name is here is F underscore C underscore EP2. Similar way, we have the other mapping numbers for all the subsequent nets like this. So let me just bring my mouse pointer. So these are shorthands and these will be used in the entire SPEF instead of the full net names. And here you can see this is a hierarchical net name. So when all these long text or alphabets, you can count how many alphabets are there. They are replaced by only 3 digits and 1 asterisk. So that will help the reduction of the entire file size. So if you have to know in a resistor or capacitor about this particular net, you have to come back to the name map section and you have to follow this lookup table to know what is the corresponding net name. Later, these shorthand are used instead of the large net names as like star:509:16538 means an internal node of the net F underscore C underscore EP2. So guys, we are done with this particular slide. So let's move on. Port map section. The chip talks with the outer world with its pins, which act as ports to exchange the signal between the internal circuitry and external world. These are captured in the port section. Let us have a look to the port section. The port section is simply a list of top-level ports in a design. The direction of the ports are marked with I, O or B for input, output or bidirectional respectively. So these will be always in upper caps, this I, O or B. Now let us see one short and sweet example of the port section. The section start with star, then ports, it will be on all caps. Next we have star1, then I, star2 as I. So all these are ports. And we have star3, the value is O. The star4 has value O. Star5 has value O. Star6 has value O. Star7 has value O. Star8 has value B. And star9 has value B. So please don't confuse this I and O with 1 and 0. So these are I and O. Whatever you have in the port section, those are I and O on the right hand column. And don't confuse them with 1 or 0. So let's move on. The DNet section. The largest part of the SPEF file is the RCC section, which is subdivided into DNet, that is D underscore NET, then CONN, CONN, RES, RES, and CAP, CAP sections. In this slide, we will talk about the DNet section. DNet means the distributed detailed net. Sometimes in RSPF format, there can be a similar section of RNet, that is R_net, meaning the reduced net. Let's now focus on the DNet section. Each extracted net will have a DNet section. This will contain a DNet line that start with R, then in all caps D_net, a CONN section, a cap section, a raise section, finally an star end line to end the concerned net section block. So the DNet starts with star D_net and ends with a star end. In between it will contain the CONN, cap and raise sections. Single pin nets will not have a raise section. Nets connected by abutting pins will not have a cap section. The DNet line tells the net name and the net's total capacitance. So when this DNet line is there, the last field will contain the total lumped capacitance of this particular net. The capacitance will be the sum of the all capacitances present in the star cap section. So this lumped capacitance is the sum of the all capacitors present in the cap section. The CONN section, the connectivity of a net specified in detail in the CONN section. This section is very important for the STA as well as the EMIR tool. So let us get familiar with the CONN section. The CONN section lists the pins connected to the net. A connection to a cell instance starts with a star I. A connection to a top level port starts with a star P. The syntax of CONN entries is star I, then we have the field pin name, then we have the field direction, then we have star C, which follows next two values, that is X and Y coordinate, and finally we have the loading or driving information. So it could be either loading or driving, cannot be both at the same time. Where the pin name is the name of the pin as per the design. The directions could be I, O or B as per input, output or bidirectional signals respectively. The XY coordinate will be the location of the pin in the physical layout. For an input, the loading information will be star L and the pin's capacitance. For an output, the driving information will be star D and then the driving cells type. So we have the short and sweet description of the CONN section here. Now we are done with this particular slide, so let's move on. The raise section. This section have resistor details. Resistor due to the metal or via both come under this section. During extraction, if you turn on the tail comment to be dumped, then you can identify a metal or a via simply by its layer number from the additional layer map section coming just after the name map section. We will talk about the layer map in the last slide of this presentation. Now let us focus on the raise section. The raise section provides resistance network for the net. Entire entries in the raise section contain below fields: an identifying integer, two node names of the resistor terminals, resistance value between these two nodes. So one single raise line will contain these things: an identifying integer, two terminal node names, and finally the resistance value. The raise section is very much important section for the EMIR analysis. For EMIR analysis, the tail comment is a must. For STA, it does not matter whether we keep or remove the tail comment. We are done with this particular slide, so let's move on. The cap section. The cap section contains the simple capacitors and coupling capacitors. This coupling capacitor is very much important in signal integrity and crosstalk analysis. For STA, this section contributes the RC delay calculation of the metal or via interconnection routing. Let us take a tour of the cap section. The cap section provides detailed capacitance information of the net. Entries in the cap section come in two forms: capacitor lumped to the ground and a coupling capacitor. A capacitor lumped to the ground has these below fields: an identifying integer, a node name, and the capacitance value of this node. A coupling capacitor has four fields: an identifying integer, two node names of the two end terminals, and the value of the coupling capacitor between these two nodes. So we will discuss this through an example. All of these sections, all these things will then come clear into your mind. We are done with this particular slide, so let's move on. RCCC section example. We have discussed the theory so far. Now let us dig into the example. Here is our DNet line. There are three fields. The first field of the DNet denotes that this is the beginning of a denote block. So here it is the beginning of the denote block. The next field is the net name, including the hierarchy. The hierarchy separator is / here. So this is the hierarchy separator and this is the node name final. This field can also be a number if the number is mapped with this net name in the name map section. So if we have a mapping of this particular net, so it could be a number instead of the name, and then there will be the node name. This last field denotes the total lumped capacitance of this net. Unit of this capacitance have to be obtained from the header section. This line starts the CONN section, that is connectivity section. This line gives the first connectivity information of the concerned net. Here, this I refers to the internal pin. The pin E and the total hierarchy up to E is also included in the name. The next field I, here you can see the I, means it's a input pin. The next field *C means that the next two fields are X and Y coordinates. So this is X coordinate and this is Y coordinate. The *L means we have a loading value. The next numerical value is the load value of the pin. This is the input load of this particular pin. This next line is very similar to the previous line we have just discussed, and this is for pin A. And here you can see that up to this the hierarchy is, and here it is I, and here the X and Y coordinates, and here is the load capacitance value. In this next line, we see a bit of difference. Let me explain. The pin name is Z. We can see the hierarchy down to Z. Here we go down hierarchy to Z. The next field O means it is an output pin. Then *C denotes the next two fields are X and Y coordinate. This is X coordinate and this is Y coordinate. These are coordinates in actual layout. The next field is *D. This gives the driving cell name of this pin as the next field. Here the driving cell name is OR2M1P. So this is the driving cell. The next line starts the capacitor section. This means the *Cap starts the capacitor section. In this section, we will encounter capacitance and coupling capacitances. The normal capacitances has only one net name followed by its capacitance value. The coupling capacitance has two net names in between which the coupling capacitance is connected and calculated. The coupling capacitance numerical value will be the last field of the line. The first capacitance of the cap section is a simple capacitance. The first field is the capacitance count number, which here starts with 1 and it is incremented by 1 for any subsequent capacitors. You will see as the example proceeds. The next field in the line is the net name including the pin name with a colon separated at the last. This field is a number. Then it will denote an internal node instead of a pin, which is usually an alphabet. So here instead of an alphabet, if we have a number, it will denote an internal node. The next field is the capacitance value for pin or node, whichever is applicable. This is the capacitance value. This is the lumped capacitance value or the capacitance with respect to the ground, because this is a simple capacitor expression. The next capacitance, we can see the first field is incremented by 1 and it has become 2, as I just mentioned. Here we have two net names. One has a pin name A, another one has the pin name Z. If we had numbers instead of A or Z, that would mean these are internal nodes. The last field gives the numerical value of the coupling capacitance. So this is the coupling capacitance in between these two nodes, or pins here rather. And the example before, it was the lumped capacitance with respect to the ground. So here is the difference of the two kind of capacitance expression. This next capacitance again is a simple capacitance to the ground. You can interpret this as same as before. The next line, that is star res, denotes the beginning of the resistor section. Here in this line, the first field is the identifier, also known as the counter, which increments by the value 1 for any further subsequent resistors. The next two fields are two nodes in between the resistor is connected. So this is node 1 and this is node 2. Here in this case, these are two pins. In case these E and Z are integers or alphanumeric value, they will denote a node instead of pin. The last field here is the resistor's numerical value. The unit can be found in the header section. So the resistance section is very much simple, at it has only one particular format, that is two nodes in between the resistor is connected and the last field is the resistance value. The next resistor has the same format as just we have discussed. And again, this has the same format too. Here comes the star end, which ends the dnet block that we started with the dnet text. Here we started the dnet block with this d_net, and here we end this particular dnet block for this particular net with the star end. So this is the opening and this is the closing of the dnet block. Before concluding here, few more things I would like to mention. When a metal routing is breaking into several pieces, it creates multiple resistors. Now this breaking into is done by the extraction engine. No designer does this, but the extraction engine, for its calculation purpose and the algorithm, it breaks it down for a long metal piece into multiple shorter metal pieces, which are also represented as resistors. Such two neighboring resistors will have one node common in between them. Their order may be anywhere in the entire res section or the block, but the common thing will be they will have a particular node common. So if you see such resistors inside a single res block, you will understand this is the two section of the same metal routing piece. For EMIR, we dump additional tail comments of all the R, P or CC, that is resistor capacitance and coupling capacitors. From this tail comment, we also get the XY coordinates in the actual layout. For resistors, we get the metal or via layer number also. We are done with this particular example and we can move on to the next slide. Standard parasitic extraction format snippet. Here we will go through a miniature version of a SPEF file. Okay guys, one thing to be very frank here, we cannot quiz an entire SPEF file in a single slide. I have tailored it and removed the bulges and make it oversimplistic for you just to grasp the entire SPEF in one single shot into your mind. Here is our total SPEF file. This is a snippet. This is not a real SPEF file. This is just for your understanding and educational purpose. Here is the snippet we included in the layer map and the tail comment, which are interdependent. Here you can see that we have the header section, then we have the name map section, then we have ports, and this layer map section is contributed by these tail comments. Whenever we put tail comments, we get this layer map. Then we have a dnet section, which has the con, cap, and the res section we have just described sometimes back. The purpose of this slide is just to imprint the SPEF file structure into your mind. Let me rephrase again. Here goes our header section, then comes our name map section, then comes our port section. The layer map section comes the next. This is associated with the tail comment. Whenever the tail comment is there, we need the layer map, otherwise we don't. Next comes the dnet section. in which we have subsections as con, cap and res. And here you can see that if there is a LVL, it is 23, means here if we go back to layer map, it will point out that here 23 is metal 2. So this register is metal 2. Such tail comments, and again I have trimmed it down. There will be XY coordinate values from which you can actually go to the layout. And since this is a metal piece, there will be W and L, that is, it will be a rectangular piece. So length and width, this is length and this is width. So if it is a via, then instead of W and L, here will be A equal to some value, that is the area. For vias we have area because vias are square generally. I think I have given enough details about this snippet. Hello and welcome to the 9th episode of Static Timing Analysis. In today's episode, we will discuss about the SDF file in a nutshell. The full name of SDF is Standard Delay Format. We have seen other files to contain the delay information of various kinds. All other files contain delay as a whole or the entire standard cell library or the entire sea of interconnect. They may have surplus information with respect to the design under consideration. SDF contains all sort of delay information in a compact fashion specific only and only to the design. Another beauty of SDF is that this is a file that can be generated in multiple stages of the ASIC design. We can take a SDF generated at synthesis stage to PNR, and opposite direction is also true. Even we can take SDF generated at post-layout STA back into the pre-layout STA. So in a nutshell, SDF file can move back and forth in the entire ASIC design flow. So here goes our today's menu. Introduction to the SDF file. Next is what is inside the SDF file. Limitation of SDF file. SDF file structure, that is header, tail and timing sections. Next is SDF file description of each section. Next, example of SDF file, a snippet. Finally, we talk about another file, that is TWF file in a nutshell. So here is our menu for today. So let's begin. SDF introduction. Now let us have the biodata of the SDF file. Standard Delay Format SDF is an IEEE standard for the representation and interpretation of timing data. It was born with OBI standard, later ported into the IEEE standard from version 4.0 onwards. It is an ASCII format, that is human readable file. It creates a bridge between dynamic and static timing analysis. SDF file includes path delays, timing constraint values, interconnect delays, and high-level technology parameters. It has usually two sections, one for the interconnect delays and the other for cell delays. SDF is compatible for both back annotation and forward annotation. So we are done with this particular slide, so let's move on. We continue here. Let's complete the biodata of SDF file in this slide. Throughout the design process, you may use several different SDF files, because the reason already I have said that many EDA tools can generate the SDF. So one may be generated at the synthesis level, another may be generated at the STA, another may be generated at the PNR by different tools. They may be from the same vendor or maybe from a different vendor. And the beauty of SDF is that it can be done a backward annotation and a forward annotation. So that means you can take a SDF from the PNR stage and come back to the synthesis stage. So that's why you will face different SDF files. And another thing also, when there is a big company, there will be multiple design teams. One design team is working at the synthesis level, another may be working at the static timing analysis, another team may be working for the PNR level, and so on. So each team may be using also a different software, maybe from different EDA vendors. That is the reason you may face various SDF files in the entire ASIC design flow. The data in the SDF file is represented in tool-independent way. It can be well understood. Just now I have said that SDF file is generated by multiple tools and they are from various vendors. That's why the SDF is tool-independent format, and it is basically right now in a IEEE format. Some of these files can contain pre-layout timing data. As I've already mentioned that maybe it is generated from the synthesis stage or maybe from the pre-layout STA, then obviously it will contain the pre-layout data. If it is generated from the post-layout STA or PNR stage, then it will contain the post-layout data. While others can contain path, constraint or post-layout timing data. So this is basically the fact from which stage the SDF is getting generated. So at that stage, whatever the data is unique from the any other stage will come to the SDF. The name of each SDF file is determined by the EDA tool. So each EDA tool may create the SDF file with a different name. Generally, there must be a thumb rule that if you are working at the STA level, the name may contain the text STA. If it is generated by the PNR, it may contain the text PNR. The conventions are different from one company to another company. There is no naming convention for the SDF files. In general, there is no thumb rule how you name a SDF file. This may be from a convention specific to a company, or you may write the name as you like or as you can identify. So we are done with the SDF introduction. So let's move on. What is inside the SDF file? To describe the SDF in vivid detail will cause multiple episodes. So in this episode, we will have a compact idea of the SDF file. In this slide, we are having a bird's eye view of the SDF file. So here we go. A SDF file may include any or all of the below things. Delays of module path, device, interconnect and port, incremental and absolute delays. That's all the kinds of delays can be inside the SDF file. Next comes the timing checks: setup, hold, recovery, removal, slew, wait period and no change. So all these types of timing checks can be included inside the SDF. Timing constraints: path, slew, period, sum and diff. So all these type of timing constraints can be included in the SDF file. Timing environment: intended operating timing environment. Scaling, environmental and technology parameters. The scaling, environment and technology parameters may come from the PDK and other things. All this other data can come inside the SDF. We are done with this particular slide, so let's move on. Limitation of SDF file. In this slide, we will discuss the boundary conditions with which the SDF file have to operate. This will give us the realistic picture of the SDF file. Here we go. An SDF file contains timing data for a specific design. This is very important because SDF is not for the entire standard cell library. It is not for any other designs, and to be very precise to the point, a SDF is specific to the design on which you are working. Other design, if you go, the SDF file will be completely different. For one particular design, one SDF will be there. Now, this SDF for in the ASIC design flow can be generated at different stages, but they will have some common things and there will be some uncommon things as per the stage where they are designed. The contents of the file is very much specific to a region of the design or specific to a whole design. Now this another point should be taken carefully, that SDF may be for a region. That means it could be for a design block. Already we have spoken for the whole design. The SDF annotator cannot annotate if there is mismatch between a design description and its corresponding SDF. The naming of the objects must be consistent in these two places. So the naming convention must be consistent, otherwise there will be a mismatch. Therefore, changes to the design generally require the rerun of a timing calculator to generate the SDF file. Inside the design, if you have changed something, maybe its hierarchy, maybe something addition, some subtraction, anything, or maybe renaming of any port or anything like that. So those all things cannot automatically come inside the SDF. SDF has to be manually generated by the user. During annotation, inconsistencies between the SDF file and the design description are considered as error. So the annotator tool checks between the design, maybe it's a Verilog description, synthesized netlist, or maybe I've already done a PNR version of the design. So if there is inconsistency between the SDF and that particular design or in format, the annotator will lag out an error. So these are the realistic boundary condition of the SDF file. We are done with this particular slide, so let's move on. SDF file structure. As we have already mentioned that the SDF have the design specific data only. Now let us look into how this is organized inside the SDF file. Here we go. First, there is a header section. We continue downwards. Then there will be cell 1, cell 2, cell 3, all the cells that are picked up from the standard cell library for this particular disk. Those picked up cells will be here. We'll explain all of these things upcoming slide with definition plus example. So we are done with this particular slide. So let's move on. SDF file, the header section. The SDF file have a header section and it do not have a footer section. So let's get familiar with the header section now. The header section of an SDF file contains information that relates to the file as a whole. This header section is a kind of identity card for the whole file. Most sections are documentation purpose only and do not affect the interpretation of the data in the rest of the file. So these are basically maybe comments and for the end user to read it, just for the identification purpose. Key sections that impact interpretation are hierarchy divider and time scale. So here this hierarchy divider and the time scale, these will have some impact on the tool and the design. So this is in a nutshell what is the impact of the header section. So let us move on. We have some further details for the header section remaining. Let's cover it up. In this and the next slide, we will have a short and sweet description of the header section using tabular data. Here we go with our table. So let me bring my mouse pointer here. It has come. So SDF version is here. There will be a tag of SDF version. What it means, the SDF version is the entry identifies the version of the standard delay format specification for which the file conforms. So it will contain the SDF version, then Q string. Q string is nothing but a string, that is text. Design name. The design name entry keeps the record of the respective design to which it belongs to. So you have a design, probably as per your company, you have given it a name. So that name will be here. So design and then Q string. Q string means, again I am saying, it's a text. Date entry records the date of creation of the SDF file and it is also date and Q string, the format. So this is a very important entry because when we are going through the entire ASIC flow, sometimes you have to multiple time iterate and multiple time you have to generate, right? In case you face the same name of the file in two different locations, how do you identify they are same or different or they were generated on the same day? So this field will help you. Other than that, you can do a GVMD for TKD to find out the content difference. That is fine. But how do you know that which date it was generated? Date entry will help you to get that. Vendor entry. This keeps the record of the manufacturing company. It's also the format of vendor and Q string. So the company in which you are working, that name will come here. Program name keeps the record of the parent software program which creates the SDF file. So as I said, right, the SDF can be generated by any step of the ASIC flow. That tool which is generating the SDF file, that name will be kept here. Format is program then Q string. Q string is nothing but a text. This will help you to identify at what stage this particular SDF is done. So if it is generated in the synthesis stage, the name of the synthesis tool will be here. It is generated in the pre-layout STA, then the tool name will be there. If it is generated in the PNR, then the PNR tool name will be there. Like this, whatever program has generated the SDF, the name will be there. We are complete with this table and we are having another table like this in next slide. We continue the table in this slide. Here we go. So let me bring my mouse pointer. So here is the program version that keeps the record of the parent software program version. So yes, maybe a design cycle is taking 7-8 months. Generally after each 3 months, EDA tool vendor releases a new version of the program. In case you need to confirm which version of the same program you have used, so this field will help you. So syntax is version then uString. Hierarchy divider. This records the hierarchy separator. Limit is 2 characters. So syntax is divider then hchar. This is nothing but alphabets. 2 alphabets will be there. It may be slash or colon, whatever. So this hierarchy separator is nothing but if you have a hierarchical design from going from the top level to the block level, you need to go through a lot of hierarchy down to the last smallest block. So all those hierarchy are separated by the hierarchy separator. Voltage entry. This records the voltages for which the SDF data generation has taken place. So here the format could be voltage then RTRIPLE. At some later slide we will describe about this RTRIPLE. It is nothing but 3 real number separated by colon. Then another syntax could be voltage then R number. Process entry. This records the process for which the SDF data generation has taken place. It is the process and the uString. Temperature entry. This records the temperature for which the SDF data generation has been taken place. So as we know that I am talking about these 3 things, voltage, process and temperature. If you can see, generally we have different PVT corners for which we optimize the design. Those PVT data will come through this process, voltage and temperature entry inside the SDF file. You can identify at which PVT corner this SDF is generated. Then we have the timescale entry. This specifies the timescale entry which is globally applicable to any time entry in the entire SDF file. So here the format is timescale then TS value. So here will be the timescale value. So if you remember that in Verilog file you have a backtick timescale where you define the timescale, right? The same thing will come here. We are done with this particular slide, so let's move on. SDF file, cell and its type. So the design is synthesized using standard cells. The library of standard cells is huge, but a subset of the entire library used in the design comes into the SDF. We can get the delay of these cells in the cell section. Let us see how this data is organized in the cell section. A cell entry represents either a region or a scope within a design. For example, a 2-input NAND gate or a flip-flop. So these could be the instances of the cells from the actual standard cell library. Hence, they can be region. Physically, if you look into the layout, any cell is basically a region. And programming or coding wise, it could be called as a scope. So I explained these 2 lines. Now let's move on to the third one. Data is applied to such library-specific regions in the design. The data will be very much specific to the region. This is the property of SDF or limitation of SDF or boundary of SDF, whatever you call. The syntax is cell, then cell type, then it could be a cell instance or could be timing spec. So they are marked in bold. So this is the syntax. We will see some examples later. Cell type. The cell type indicates the name of the cell. Why then we call cell type? Why not name? Because the cell type means, say in standard cell library, there will be different types of cells. It could be a combinational or sequential or special cells. So that's why it is called cell type and not a cell name. So it's more generic in that sense. Syntax, cell type, then uString. That means a text. uString, I think it's maybe the quoted string. That means within the quotes it's the string. That means it's basically a text. The examples like cell type, then DFF, D flip-flop, cell type top, it could be top of the design, cell type buff could be the buffer. So this way, these are the examples. We are done with this particular slide. Let's move on. Cell instance. A single standard cell can be instantiated in multiple zones of the design. According to the placement, we may or may not have the same data of a single cell. To deal with such cases, we have the cell instance section. Let us see how this is defined in SDF. The cell instance targets the specific instance or wildcard instances on which the timing data is to be applied. Syntax is like instance then path or instance then wildcard. Okay, we'll see with the examples, we'll understand how. And instance means it's at the down the hierarchy up to a block or inside, even go inside a block. So path comes from that factor. Example, cell, then we have cell type DFF, then we have instance, then A1.B1.C1 and we go on. Here the dot is the hierarchy separator. A1 is the topmost block and C1 is the instance. then again cell, then cell type DFF, then instance, then tar. So in the first case, the SDF data, annotation data will be specific to the instance C1. So it is very much specific to that instance. And in the second case, here when we are using the wildcard, the SDF annotation data is generic. That means the same data can be applied anywhere with the cell type DFF. So we have done the explanation and let's move on. Now we plunge further down inside a cell for the timing related data. In this and upcoming slides, we will unfold the timing section inside a cell or cell instance. Here we start. Timing specification. Each cell has three types of timing information such as delay, timing check, and timing environment keywords. Syntax is for delay we have del type, for timing check we have timing check definition, and for timing environment we have timing environment definition. Delay keywords represents the associated delay values of input to output paths, input ports, interconnects, and device outputs. All of these are considered under the delay keyword. We are done with this particular slide, so let's move on. Timing section, the path pulse. When a signal passes through a cell instance, we have a checkpoint depending on the pulse width. This is path pulse. Here we have two pulse width thresholds which a signal has to satisfy to cross the cell. These thresholds have unit equal to the time unit of the simulation. So let's start. The path pulse entry represents the narrow pulse propagation limits associated with a legal path traced between an input port and an output port of a device. These limits determine whether a pulse or a certain width can pass through the device and appear at the output. So this is basically having two threshold criteria for one particular cell where there is an input port and there is an output port. If the pulse satisfies the two thresholds, it will pass through it. So here goes our example, instance, and then we have delay, then we have path pulse, I1, 01, then 13 and 21. So here let me bring my mouse. Instance, I have marked a generic X here. Okay, it could be any instance, and the path pulse is between the input port I1 and between the output port 01. The first threshold for I1 is 13 into the time units as per the header section, and for output the threshold is 21 multiplied by the time unit, and the time unit can be found in the header section. So thus, the path pulse is defined. Now, let us see some more examples. Instance X and then delay and then absolute, IO path, close. Okay, we come again to the path pulse statement. We are not discussing about the delay, absolute delay or everything. We will discuss it later. So, the path pulse here again between A and Y, and the two thresholds are 13 and 24. Each can be multiplied with the time unit and the final value will be the threshold. Path pulse of BY is 15 and 21. So the path pulse between the input node B1 and output node Y is the two thresholds are 15 and 21. And here we close it. So this is in short and sweet description of the path pulse. Here we come to the next slide, path pulse percent. The path pulse percent is another type of representation in forms of percentage. The rest of the idea from the previous slides remain the same, except here it is the percentage. Let us see. The path pulse percent is an entry is same as the path pulse, but the values are expressed as percentage of the cell path delay from input to the output. Here goes our example, instance X and delay, and then we have absolute delay, IO path, cross, and now we come to the path pulse percent, that is between A and Y is 25 and 35. Format I have already explained, so let's move on to timing section, absolute delay. Now let us see how absolute delay values are organized inside the SDF file. So last couple of slides we are seeing the absolute and the delay. Okay, now let us discuss about this one. Here there are two placeholders. Let's start. The absolute keyword introduces delay data that represents existing delay values in the design during annotation. Cell type, here goes our example, cell type is DFF. Then instance is A.B.C. Then we have delay, and then we have absolute, and then we have IO path, then posage and clock, and then Q. Then we have two RTRIPLE format, that is trivial number separated by colon, and such two set of data is there. So for port CLR, we have again to RTRIPLE format, and here we close and close and close. So this is the absolute delay. So this IO path and the port, these are the values of the delay. Now just pause here. This RTRIPLE format needs to be described in detail. So wait for that. First, you see how this is written inside the DFF. Next, we go for the explanation. So here we have another instance, delay, and then we have absolute, then we have port R1.A, and then we again have the RTRIPLE format. And then again we have another port that is R2.A, and we again have the RTRIPLE format. So difference is between that, in the left one case, in the yellow box, we have from one particular pin to another particular pin, and like passage of clock to Q. And here in the right hand side, we have a single particular port. We also have a port in that left hand yellow box, CLR. For that we have RTRIPLE format, but here also you can see that here only the things are two ports. We close it. We will explain the RTRIPLE format in the next slide. So let us move on. RTRIPLE format, let us discuss. We have just seen the examples where there were t numerical values separated by colon and packed together using a pair of parentheses. Now let us see how the interpretation comes for these ones. When a single value is used, it specifies the delay value. When two values in parentheses are used, the first value specifies the delay as if a single value were given. The second specified both the pulse rejection limit and E limit associated with this particular delay. When three values are there, the first specifies the delay, the second specifies the pulse rejection limit, and the third specifies the E limit. So if there is a RTRIPLE, the first one is delay, second one is the pulse rejection limit, and third one is the E limit. If there are two values, then the second bullet will be applicable. And if there is one value, the first bullet here in this page will be applicable. Each value is either a single real number or a RTRIPLE containing three real numbers separated by colons in parentheses. Just I have explained. So I think we are done with the RTRIPLE format in this particular slide. So let's move on. Increment delay. Here we will talk about the delay values which are appended to the existing delay values upon the annotation. This means here we are talking about such delay which will sit on top of the existing delay when we annotate. The increment keyword introduces delay data that is added to the existing delay values in the design during the annotation. Here we go with our example. Instance A.B.C. Then we have delay, and then we have increment, and here we have the IO path. Then we have passage of clock to Q, then 4::2, then -7::5. And here we have port, one particular port, CLR 2:3:4 and 5:6:7. We close it. Close and close. So here you can see this increment keyword. Let me bring my mouse on. Yes. So here everything is same here as with the previous example, except this difference. This increment keyword is here. This means whatever the delays coming out of these expressions will sit on top when these are annotated with existing delay at that particular stage where we are injecting this SDF. So I think we are very much clear on the incremental delay. So let's move on. Example of SDF file, a snippet. Since we cannot squeeze a whole SDF into single slide, hence we have trimmed it down in this particular slide. Hence we call it a snippet. Here is our left box and here is our right box. In these two, we will try to stuff one single SDF in a very miniature version. So here goes our header section, delay file, then SDF version, then design top, then date, then time, vendor, program, which program we are using to generate it. Here we have version, and here we have divider, and here goes our voltage, process, temperature. So the last three entries are PVT entries: process, temperature, and voltage. Also we have the hierarchy divider just above that, that is dot. Time scale is 1 nanosecond. This is same as the backtick time scale. So cell, and then cell type XOR2. Here starts our cell, and instance top.x1, and here we go for its delay, and we have the increment, and we come with our statement inside it. CONN this condition, So count 2 here and we go continue, and finally we continue, and here we close. Here we have just tried to keep a snippet of the entire SDF file in a short and sweet fashion. So conditions we have not, it's like a if else then condition. That's all with this particular snippet. I have nothing more to say on this. So let's move on to the next slide. So this slide is not from the SDF, but here we talk about TWF file in a nutshell. One of our viewer requested to put the TWF file in STA series. Now let us see the TWF file in a nutshell. Some of the STA tool can generate a TWF file which contain information about switching window and transition times, both of which have a large impact on dynamic power. So this TWF file will contain about the switching window and transition data. Equal command to write out the TWF file is write_TWF then file name. So this is basically, it may be a vendor specific. When I was looking for TWF file, I came across that it is a very vendor specific file, and in that particular vendor you can write it with the write_TWF. TWF contains timing window and slew data. Tool finds the earliest and the latest arrival times for each victim net and aggressor net. The range of switching times between from the earliest to the latest arrival defines a timing window for victim net and defines another timing window for the aggressor net. So all of this data you can find inside the TWF file. Crosstalk effects occur when the victim and aggressor windows overlap. So this is the outcome of the data that you can interpret from the TWF file. So that's all folks. We're done with this particular slide. Let's move on. Thank you very much for watching up to this point. And don't forget to like, share and subscribe. If you have some kind of dislike, put that in as word in the comment section below. And bye for today.